Thank you. So I'll start out with just what I won't talk about. There's been some really great talks about doing detailed modeling, looking at reverberation mapping, getting really reflection, coronal cutoffs, soft excess. People haven't mentioned ultra-fast outflows, but I won't talk about that, or covering factor, and also sort of radio loud AGN and blazars. And then the other thing I want to do with my talk, because it's really on AGN surveys in general, is focus on what can we do with the wide field monitor. And I started writing this presentation, and then a few days later I started reading all the white papers from Loft, and I was like, wow, there's a lot of great stuff that's already been done. So I've incorporated some of their work and some of their work simulations, because particularly with WFM, it's sort of the same instrument. What are the big questions I think we can answer with STROBE-X? I think that the biggest thing to me is really the obscure black hole growth with the LAD, and also detecting these sources. And then we can do all sorts of interesting studies in terms of the host morphologies. And then the other point I think is the distribution and really the column density of the material by looking at variability in terms of timescales of days and months, and how do AGN really vary sort of with the radio to the X-rays, and also optical to X-rays for large samples. So this is actually from the AGN white paper. It's a simulation of sort of the 1-year sensitivity, showing the exposure time here versus the total number of sort of expected AGN. So there's really several hundred AGN that you get in the first year with at least 10 data points to do light curves. So this enables a lot of different studies in terms of the variability of luminosity, variability in terms of the how it relates to the Eddington ratio, and you can do it on a wide scale of both soft and harder energies. So the overlap, this is something I stole from my Links Synergy group, but in the survey context, so I'm guessing we'll be somewhere sort of in the late 2020s. I think the important things that, in terms of overlap, are going to be the LSST, as well as the SKA, which will be sort of picking up, and the CTA. So there's real synergies in terms of looking at the X-rays versus the radio, and let me talk a little bit about those. Actually, that happens in one more slide, but one of the things I want to talk about in terms of the NH variability we can study with AGN surveys is, so we know that a lot of these nearby AGN, there's dozens of these that have very, and this particular one we're showing at high energies, as you see 49, 45. And this is one area where the LAD is really the instrument to use, because it's going to be more sensitive than NuStar. And also with the wide field monitor, we could imagine looking for sources that vary in sort of the 3 to 10 keV range that have smaller column density variability. And the important thing here is that eROSITA will map the sky, but it'll only do sources kind of every 6 months. So you're not going to have the capability to find these sources that have these sudden changes in column density. And this is just showing an example, for example, if you had some sort of eclipse and how it might change the iron line region. So I think that gives us some real capabilities to understand what the material is and how common it is that this material is actually moving in front of our line of sight, and in general, what is the sort of column density of these absorbers and their size. Another interesting thing, which was mentioned by Mislav, and we've been working on doing this at high energies, but it's really hard to get the power spectral density at high energies, because you're trying to use sort of NuStar plus BAT, to do the long-term monitoring. And we think it sort of agrees with what people have found at softer energies, but this is something that one could do much easier with the LAD and also the wide field monitor. And when you have these things, as was mentioned by Tom, you can look at where the break is, get an estimated black hole mass from that, and compare it to masers, and really try and get good estimates of black hole masses for nearby AGN. There's also a lot of stuff you can do in terms of radio variability with the SKA. So for radio quiet AGN, we know there's some emission, but we're not exactly sure if that's related, how that's related to the X-rays. And that's something that we could do in a fairly large survey, as well as with the LSST, looking at sort of accretion disk variability in terms of the optical to the X-rays. So now I'm going to switch topics a bit and talk a bit about LAD and then come back to the wide field monitor. So a lot of my work is done on the SWIFT-BAT survey, which is an all-sky survey. And so at 105 months, this is, our paper hasn't been released yet, but this tells you a bit where we are in terms of the, if you convert to 2 to 10 keV sensitivity, we're sort of about right here. So this is the LAD taken from loft, so this isn't perfectly accurate. But it gives you an idea that the sources that we have in BAT are the sources that you can study with fairly high signal to noise with the LAD. So to give you an idea of where what types of sources these are, so this is the galactic plane. And if you move off the galactic plane, you typically are looking at these nearby Seaford AGN and some small fraction of beamed AGN. So to put this into a larger context, this is just a pie chart here of the 105-month sources. Some of them we haven't had a chance yet to identify using optical spectroscopy and soft X-ray follow-up to really figure out the counterpart. But the majority are these nearby sources, typically at redshifts less than 0.1. And you can see the distribution here. This is for the 70-month sources where we really did a lot of optical spectroscopic follow-up. So most of these sources are sort of at low redshifts. And the interesting thing, I think this is important, people sometimes forget that when you do an all-sky survey, you really do sample these very high luminosity sources that are similar to what you find in these small area distant AGN surveys. So they have similar luminosities. They may be very different environments, but you're able to study these very high luminosity sources. I should say these stars here are actually beamed AGN, and then these colors and data points correspond to the different deep surveys with Chandra or with XMM. And the other point to notice is that there really is a gap in here between the surveys. Now, eROSITA will do a great job of filling that gap in, but it's not going to be sensitive to these really highly obscured Compton-thick AGN. And I need to work more on sort of figuring this out, but I think based on some of the sensitivities here that we should expect at 4 to 10 GeV, if you take that as sort of the intrinsic luminosity and you look at how deep BAT can go, that we can go about a factor of 5 deeper in terms of intrinsic luminosity. Now I think I need to do some more simulations to think about if you did an iron K alpha study, how far you could go. But I want to motivate why I think we need to learn more about obscured AGN, because even in nearby sources, we really don't know anything about this population. So this is taking a Z of 0.01 NGC galaxy, so that people have been studying for decades. And it's Compton thick, it's NGC 3393, and just redshifting it out and figuring out what whether you detected in different surveys. And so with that, you detect this about the Z of 0.02, if it's unobscured or obscured, and then you start to miss it. And with NuSTAR, you can detect the source out to Z of 0.1 to 0.2. And now if you take the Chandra 4 megasecond deep field, some of the deepest observations we have with Chandra, you can detect the iron K alpha line, so you can get its intrinsic luminosity out to about 0.15. But if this source were unobscured, you could detect it all the way out, to redshift 3 to 5. So we are very, very good at detecting unobscured AGN in X-rays. But for detecting competent thick AGN, we know almost nothing. I mean, they're really hard to detect. I mean, I think sometimes people forget, they assume we know everything about nearby galaxies, but we have all these NGC galaxies that, we're finding competent thick AGN with NuSTAR, with that, and, okay, thanks. So this high energy selection is really important, and I'll show you another slide with this compared to STROBE-X, but basically, so this is Rosat, and this is the count fraction remaining. So as you go up in NH, obviously with Rosat, once you get to 10 to the 22, you're going to miss basically 90% of your sources. This is true also really for E Rosea. It gets a bit farther, to 10 to the 23. So with Chandra, you can detect high redshift AGN where your energy is sort of band shifted into the softer energies, but it doesn't do that much better in terms of really where you're going to be heavily biased. And what really helps is to go to sort of either NuSTAR or go to SWIFT-BAT above 10 keV. Okay, so to motivate what we might do with STROBE-X, one of the things that I did recently in a paper was to create this sort of spectral curvature idea, which is basically take the wide field emission in BAT from 10 to 150 keV and basically look at how much it looks like something that strongly dominated by reflection. And hopefully I can identify some really faint sources that are actually competent thick AGN. And it actually works very well, and then we followed these up with NuSTAR, which was very sensitive. And compared to that, and you can see they all have very strong reflection humps and iron K alpha lines. And I think we could do something similar on STROBE-X. Now, why this is important is what I found is I took the spectral curvature estimate, and then I said, okay, I'm measuring the black hole masses using velocity dispersions and other measurements. If I look at these sources, where do they lie? Now, the interesting thing is these are very small black hole masses at very high accretion rates. So if you take the entire sample and use this, the sum of black hole growth, at least for nearby AGN, in this heavily obscure portion is as much as the rest of the population. So if we want to understand black hole growth, it's absolutely critical we understand these really highly obscured sources. This is just another nice result. One of these sources, we had 15 kiloseconds with SWIFT-XRT, we didn't have detection. And this is much more sensitive than E Rosea could ever really go. But with NuSTAR, and something like the WFM, this source is very bright. We would expect it with the WFM to be bright in sort of the iron K alpha line. And you can see its spectra here. It has this really bright iron K alpha line and very little emission in the soft energies. So I was trying to figure out how we would do sort of a blind iron K alpha survey. So this is something that I was working on over the last few days, so I apologize for how the plots look. But what I was doing was to take the MyTorus model and put in sort of a 6 to 6.6 keV versus the total emission, and use sort of a band ratio. And what you find is that with the iron K alpha line, I should first mention, if you do this with softer energies like Chandra, the problem that you run into is with band ratios, you don't know if your source is mildly obscured or heavily obscured, and so you have this problem of knowing exactly what your column density. But with iron K alpha, similar to with what NuSTAR can do, you can detect these sources using band ratios up to very high column densities. And the other interesting thing is if you do this iron K alpha selection, you actually do better than NuSTAR and fairly close to what SWIFT-BAT does in terms of the sensitivity. So with STROBE-X, you can imagine you focusing on an IRK alpha region where you have a much stronger signal and much less background. So I'll just leave it. I said loft, that's a typo here. STROBE-X can do a lot of useful science and a really large sample of these radio-quiet AGN. I mentioned the SWIFT-BAT AGN catalog of sort of thousands of sources. And then getting this distribution in terms of NH variability on the scale of sort of weeks to months, and looking at X-ray to radio, optical correlations, and then really getting the fraction of Compton thick sources, and based on my initial results, it seems like this could be even more sensitive than SWIFT-BAT in terms of finding these Compton thick AGN in the nearby universe. So to me, the technical trade-offs are really the IRK alpha line for WFAM, and that region around there is the most important. And as the high energy sensitivity, 5 to 15 keV, is somewhat important to getting these obscured sources. PSF is not so important. We have a problem now with BAT because it's 3 to 5 arc minutes PSF that we can never figure out where the sources are, so we need SWIFT-X RT.
Is that PSF position?
This is the centroiding error. I think it's a factor of 5 to 10 better. So, and you will have E rho zeta, so you'll have a much better map of the sky. And then I think the sensitivity for this science, because AGN are a little bit fainter, to do really large population studies, you're less concerned about the field of view. It's really just this sensitivity, particularly high energy. And I think for the lad, the greater than 10 keV sensitivity to me is what's the most powerful thing to do AGN science on nearby AGN and obscured AGN. So thank you.
Okay, thank you.